We are honored to have you here, sir. As a distinguished speaker, I request you to kindly take over the session and enlighten us with your valuable insights, sir.
Thank you.
Thank you, sir.
Okay, thank you, Swati.
Yes, sir.
Before I start, I thank organizing team that they are conducting FDP of very good eminence of importance, and the area is FSS, which is nowadays leading not only in India but Europe. In this session, I'll be talking about very burning technology, and especially ISRO is working in the field of developing Navik antennas. But they are developing Navik antennas using some sort of DR materials, but their size is huge. The same antenna we have tried to make it compact using FSS structures. So before I start FSS structure, I'll be showing one or two slides, then I'll speak. I'll share my screen. My screen is visible to you?
Yes, sir.
Slide is also visible?
Yes, sir.
Okay, thank you then. My topic of today's talk is FSS inspired GNS antenna for 5G and 6G applications. FSS is frequency selective surfaces, is known with different structures such as SRR, CSRR, and ESRR. Many nomenclatures are there. But basically, these FSS are being used for two different purposes. One is the FSS structure is being designed to act as absorber. Second is the same structure may look like that it is acting as antenna, but there is a change in wavelength. Generally speaking, the FSS structure which is designed for antenna must be specific to the lambda by 2 wavelength, and FSS structure which is being designed to act as absorber is generally lambda by 4. In this Navik antenna or multi-band GNSS antenna, we have used both. We have used this FSS structure as act as antenna, as well as we have used these FSS structures to act as absorber. So I'll be basically talking about both the theory, how these theories are being applied, and how these FSS, we have not only designed FSS structure, but we have used these FSS structure to make the GNSS antenna using dielectric material. And earlier, the dielectric material, if we do not use FSS structure, was huge. The aspect ratio was very large, or we can say the profile was very large. And then using these structures, we are able to reduce it to more than 96% of the size. So that is a great, and what I feel this type of work is you will find first time reported by us worldwide. So the focus of today's lecture will be that we are designing a antenna at very low frequency. You are already aware lambda is equal to C by F. So wavelength used to be huge, very large profile at low frequencies, but I'll be showing that the same the same size, the high profile antenna had been reduced to low profile antennas using these structures, frequency selective structures. Here I'll be also telling you that the design of the GNSS is basically global navigation satellite systems. So far, the satellite systems are generally being operated and more popularly known as GPS antennas. We use three satellites, one for getting the coordinates and one for timing. So basically, it is a combination of four satellites, and then we are able to get the exact location even in centimeters. So we are basically designing these antennas for specific use of L1 band, L2 band, L3 band, L4 band, L5 band, 2.4 gigahertz band, that is Wi-Fi, 5.8 gigahertz band, that is also Wi-Fi, and for NAVIC applications. My focus will be more specific to Indian origin, and we are more inclined toward the NAVIC because NAVIC will be used for almost all toll systems which will be later on enabled using ISRO satellites. So that is my target, to design these type of antennas, because right now we are all toll plazas, they are RFID based, and we will be you are already aware that in 99 there was a war, Kargil war. So the Indian origin, they asked satellite data or GPS locations from the for Pakistanis, and the US, because US is operating the GPS system, they denied to Indian. And since that day, the India is working towards getting the or replacing the GPS features with the NAVIC. Let me see how I can help you to deal with the GPS and replace it with the NAVIC. So we have also contributed for the Indian part of it, so that we develop these type of antennas towards Atmanirbhar and self-reliant Bharat. My first slide tells you the outlines, where I'll be talking about why FSS are more important as far as GNSS antennas. When I say GNSS, we will talk about all bands, L1 to L5 bands. The mathematical understanding of frequency selective surfaces, and here in this we have made use of ZOR, that is zero order resonance, or it is also known as ENG epsilon negative, as a concept for developing frequency selective surfaces. For all frequency selective surfaces, if we are dealing with absorber, we need to develop the design using Flankett-Ford analysis. We have also used in same GPS antennas for because the GPS signal or these GNSS signals is available round the clock. So we have tried to harvest the RF energy of the GNSS or GPS to convert into 5-volt power supply, which can supply to your mobile in the remote. I'll be talking how the ENG can be connected with the DR for making this DRA profile very low profile or compact DRA. Here in this design, we have also made use of DGS. So I'll be showing some applications of the DGS, that is defective ground plane surfaces. Important part of the design is how to get RSCP in almost all multiple bands in the GNSS. And the impedance matching, when we talk about L1 to L5 band, then 2.4, then NAVIC frequency, then 5.8. So getting this impedance match is very challenging and crucial task. Next thing, I'll talk about how to improve front to back ratio in this type GNSS antennas. Then we have made use of meta-surface structures for getting improvement in our front to back ratio. NAVIC is a special case study as far as this lecture is concerned. I will try to focus more about realistic applications of this design of GNSS antenna for NAVIC in specific, which is being dealt with ISRO. If time permits, then I'll discuss about the advancement of the fluid antennas. These fluid antennas are new norms as far as research is concerned, because in fluid, you make use of fluid pumps, microcontroller devices, and you get all-in-one solutions as far as fluid antennas. These are the burning technologies and coming up technologies. And in last, I'll conclude my talk. Now, I feel that you are made aware about GNS antenna design features. GNSS is Global Navigation Satellite Systems, and we try to align our antenna design towards the frequencies spanning towards these GNSS satellites. Here, Russia, Japan, China, Of course, now India and US is placing a crucial part as far as operating and design is concerned. Here, I'll be showing you the multi-frequency antenna which we are designing. This is in our current research that only one single antenna will be sufficient enough to cater to L1, L2, L3, L4, L5. When I say L1, you will be able to see here in the PPT the L1 band specific to 1575.42 megas. L2 is 1227.60 megas. L3 is 138105 megas. L4 is 1375.91 megas. L5 is 1176.45. These are universally defined. We are not able to change these frequencies, but we need to align to these frequencies so that internationally we get aligned as far as standards are concerned. But only the thing is that at present there is only one antenna available for L1 band. There will be second antenna available for L2 band. There may be third antenna available for L3 band and so on. But our solution will be able to provide you a complete overall solution which single antenna can support right from L1 to L5 bands. The beauty of our design is that it is compact and we try to introduce anti-jamming features in our antenna. This is also a very crucial parameter that in defense, when we apply these antennas in defense, we want to have anti-jamming features in almost all GNSS antennas. Of course, the high gain is not that much requirement, but circular, right-hand circular polarization is must for all GNSS antennas. High gain, why it is not important? Because nowadays they can augment these antennas with LNA, and LNA can have the gain right from 30 dBi, 35 dBi, 40 dBi. So they can compensate antenna gain by those circuits. Application of these all GNSS antennas will be able to provide you PNT and SWP, where here the PNT are, if I say PNT, more specific terms are occurring as APNT, means assured position, navigation, and timing. And in our feature, we have added one more parameter, that is size, weight, and power requirement has been reduced. So these are the new features we are trying to embed into our designs. We are well aware that ISRO is developing its own satellite. That satellites is known as Navik. So navigation Indian constellation. This is also named as IRNSS, Indian Region NSS, which is already spelled out to you. And the frequency of operation of this Navik or IRNSS is 2.49 gigas and already available L1 band, which almost all countries are using this 1176.45 megas. Europe is also having its own GNSS system, which is at 1.1 to 1.6 gigas. US is already, right from the beginning, has these three bands, 1575.42 megas, 1227.60 megas, 176.45 megas. Of course, Russia is also leading in this domain, and it has uh, the Russian satellites are, these positioning satellites are known as GLONASS, and it has 1.602 gigas as well as 1.248 gigas. China, of course, it also has its own band, and they have the satellite system is known as BDU 1.75.42, which is L1 band, 1176.45, which is L5 band, and 12071.14 megas, that is different band. So they are also having their own positioning system. QZSS is Japan, which has recently been entered into the market of positioning. which is 1.27875 gigahertz. So these six satellite systems or global navigation satellite system already exist. So Indian entry is now new, and they want to develop their own navigational system, and they want to exit from the GPS, which is owned by US. So full trust is already there on this from the Indian government. When I talk about 5G and 6G, different bands are there. We have been also given a project between 7 to 10 gigas, and that 7 to 10 gigas is 6G, a sub 6G in band post 6G communication. We are developing fluid antennas in this particular spectrum, but they are also 6G spanning also in millimetric wave band, as well as teras band, 0.1 teras to 10 teras post 6G advanced communication system. 5G has two different spectrum below 1 gigas and from 1 to 6 gigas. So I'll be focusing on 5G as well as 6G here. This is very important slide. I have made a clear demarcation of how the absorber design parameters differ from antenna. As I already said, that you can use these frequency selective surfaces for both the purposes. You can design absorber, and you can design antenna using FSS. So here, if you see left side, size of absorber is mentioned lambda I4. Impedance matching here, because in receiving mode generally absorbers operate, so free space impedance you need to match in flanket port 377 ohm. Material used in absorber are negative material, negative permittivity, negative permeability, or negative index materials are being generally used to design absorbers. These materials are not available in nature, so these are artificially developed materials, also known as artificially designed materials. They have negative refractance. We use a flanket port. There is no dipole formation. Very important parameter is there is no dipole formation as far as absorber is concerned. Mode, resonant mode generation is there. RLC resonant circuit is there. Uh, Power is absorbed, not transmitted. So absorber generally work in receive mode. The size of liquid port is generally taken more than lambda by 4. No absorption specific pattern. Operate based on interference theory. Of course, there are certain antennas, they also operate based on interference theory to harvest larger gains. Now, as far as antenna is concerned, they are used in dipole formation mode. Impedance is 50 ohm. Size of wavelength is lambda by 2. The material is DPS double positive, positive refractive index, waveguide feed, resonant mode generation. Of course, here also X, and I'll like to specifically mention the every antenna designer or absorber designer or anyone working in our RF domain must have total control on modes theory, because this is a wonderful tool. With the help of resonant modes, we can play with antenna design parameters. That is, with the help of mode control, we can play with polarization, we can play with bandwidth, we can play with gain, we can play with radiation pattern, we can play with dimensions, we can miniaturize, we can deminiaturize. So If we know modes control, we can play with antenna design parameters. So modes generation, modes shifting, modes merging, this in specific must be known to the antenna designer. And based on most mode theory, in design itself, the antenna designer can predict how the radiation pattern will look like. It means during the design itself, the designer can predict what will be the antenna parameters. With the help of mode, he can control gain. It means the distance manipulation of any antenna is under the control of designer. He can play with radiation pattern. Where he want to radiate, where he do not want to radiate, can also be controlled with the modes. It is, of course, not to say that during the design itself, the radiation pattern in far field will be known. Of course, when we develop hardware, there are certain parameters which we will not be able to meet what design parameters say. That why there will be a change in the radiation pattern which may not be able to be predicted. But of course, there are up to certain amount the mode theory will be able to say what will be the exact shape of the radiation pattern. Both receive and transmit mode. Antenna is designed for fundamental mode, and then we can play with harmonics. Here also, when you will see the GNSS antenna design, we have played with the design parameters. Sometimes we could eliminate higher harmonics, sometimes we could keep fundamental mode, and sometimes we merge these modes, sometimes we shifted these modes. So we have also played using these FSS, DGS, and lot many other techniques for playing these parameters has been applied in GNSS design. I'll be showing you. The size of radiation box is generally taken more. I think these are all well-known parameters which everyone knows. Uh, we here the constructive interference theory is well popular for designing high gain antennas. We have also used them. So FSS is synonym, sometimes synonym to meta material characteristics. Now there are important parameters. If you see all four quadrant, mu and permittivity is different, and sometimes we have played with these material characteristics to bring it to a particular value. In specific, in this particular design, we have worked on epsilon negative material, which is in quadrant 2. So we have successfully executed these epsilon negative material design. If you see quadrant 3, this is used for absorber. If you see quadrant 1, these positive materials are being used to design antennas. So if you see left side, main parameters of absorber, the impedance matching, Zn is 377 ohm, negative refractance, TE, TM polarization. These parameters are being specifically given for quadrant 3, that is designing of absorber, loop current formation, magnetic field generation, then absorption, then making the device polarization sensitive as well as insensitive, controlling the incident angle. Here we have applied this controlling incident angle in designing of GNSS antennas. When the signal is coming from a low angle, we are able to successfully turn the RSCP signal into LSCP signal, and then this type of antenna design will be termed as anti-jamming features. So detecting low incident signals, converting these low incident signal into the other polarized signal has been effectively utilized to achieve anti-jamming features in design of GNSS antennas. Then the fourth quadrant is mu negative. So basically, when you design either antenna or absorber, you need to work on these all four quadrants, and then you can play with EM wave characterization. That is very important. So to understand the all four quadrant, to get the material specific to epsilon, specific to mu, specific to index rather, is very important. So before we design, we should know these parameters. I think this all already I have explained working of absorber. I'll not repeat this. This is those who are working in and designing ENG, DNG, they must be knowing about this, that how to create flicker port and select boundary conditions and excite modes. This is basic structure each one has to understand. This is a Plinkett port structure basically. With the help of that Plinkett port structure, we are able to create a FSS structure. So I'll say, if you see here, this is a DNG FSS structure. When I say DNG, go to that particular quadrant, and then you will be able to respond that what will be the design principle and design parameters, whether it will be a absorber or it will be a antenna, and how the mode excitation will take place. Here I am able to clearly visualize that. Of course, it is at terahertz, but I have specifically taken for the reference that how FSS are being utilized for absorption. So here, if you see the structure, there is a bottom ground plane, SiO2 substrate, FSS structure, and I have designed this FSS structure for a particular wavelength for 6G 0.1 to 10 terahertz. While absorber is designed, we need to look for S11, absorption, incident angle, polarization angle, impedance matching to free space, bandwidth, resonant modes. The heart of antenna design is to clearly create resonant modes, make them to dance as per our requirements, is the crucial role being played by the antenna designers. With the help of playing with these modes, as I already said, the antenna can be made multiple band antenna. It can be converted, same antenna can be converted to wideband antenna by merging of modes, by splitting modes, multi-band antenna. So the modes generation and control is very important as far as design parameter is concerned. Then we can realize these modes with the help of equivalent RLC circuit, and based on equivalent RLC circuit, we will be able to determine the resonances, surface currents, whether it is E field and X field. With the help of this, if you take a plot of surface current, surface density, and then you visualize the pattern of E field and H field, we will be able to particularly see which mode is being excited. We use these E field and H field plots for identifying the resonant modes. Now, very important part of my today's lecture will be this compactness. We will see that initial design I have used dimensions 60 into 60 into 40 cube, and same dimensions after applying FSS theory or frequency selective surface theory or DNG theory or ENG theory. I'm able to convert these dimensions into 25 into 25 into from 44.3 cube. Otherwise, I was dependent because as far as in Indian scenario is concerned, there are two companies, High Tech Bangalore and Sramik Ahmedabad. These two people are able to supply me the dielectric constant material for devising dielectric resonant antennas, which has a low permittivity, that is 10.8, 9.9 only. We are already aware that epsilon or relative permittivity of material is inversely proportional to frequency. When I say inversely proportional to frequency, for designing at low frequency, size of antenna, dielectric resonator antenna is very huge. But if I have material of high dielectric constant, high permittivity, my size can be reduced because frequency has relationship with the wavelength lambda is equal to C by F. I was dependent on the high dielectric constant being supplied by Transnec USA. They are able to supply me the dielectric material having dielectric constant spanning from 10 to 250, 300 farad per meter. So I was dependent, if I want to make a compact dielectric resonator antenna, I was dependent on US company Transtech. They ask all the data and then they provide me the DRA. So it is very difficult to keep your research uh, secret or isolated, because they will be asking size, they will be asking what material, they will be asking how much dielectric, everything I need to provide, then only they will be able to supply those dielectric materials. But now I can give only size to Indian companies, they will be able to give me fabricate and provide me the material. I am not depending on the foreign origin companies. By introducing a concept of compactness theory, I'll be going in detail how I am able to make DRA compact by adopting the theory of FSS or ENG. PNT and SWP, you are already told that these are the two important parameters which are required to develop GNSS antennas, which will be utilized for all autonomous vehicles, all IoT devices, all your trains, all aeroplanes. So these GNSS is very popular and most demanding article worldwide. But still, as far as India is concerned, we have limited capability to design and fabricate GNS antennas till date. That is why we have taken up this task that we will be able to devise all in one antenna which can support almost all GNSS, Wi-Fi, WiMAX, etc. Used in agriculture, used in wearables, almost all watches, they require precision positioning and timing synchronization. GNS antenna can provide these parameters such as timing, positioning, and navigation. We need to, as I already told, that perfect matching with impedance 50 ohm if we are able to, which if we are focusing to design the miniature and all in one antenna is crucially very challenging task, because you need to keep frequency ratio, you need to play with the front to back ratio, you need to play with isolation, you need to play with the desired bands, you need to avoid interference from the undesired bands. So that can only be possible if the matching for all the desired bands is made perfectly 50 ohm impedance and getting high value of front to back ratio. Getting gain, our design will be able to provide 9 dBi gain with RSCP. RSCP is very important as far as GNSS antennas is concerned. So as I already said, we have applied FSS of ENG concept, epsilon negative, and we are able to reduce the size to almost 97%. You can just think of need for high dielectric constant or high dielectric material has been totally eradicated by this FSS structure. So that is a great achievement in this particular design. Here is the structure. Now we have designed, you are able to see here it is FSS structure. This is a FSS structure, this is a FSS structure, this is a FSS structure, and this is your dielectric resonator antenna. The difficulty was that Transtech and Ceramic were only able to supply these material known as alumina Al2O3, and the permittivity of Al2O3 is approximately 10. So when we place this formulation in rectangular DRA design formulation, that is that will be given to you Fr is equal to C upon 2 pi under root epsilon r whole under root m pi by a whole square plus n pi by b whole square plus p pi by d whole square in case of isolated, and it will be 2D in case of image effect is applied, that is ground plane. I'll be giving you this formulation which I have just now narrated. So this is a structure. Here this is top structure, and in bottom structure also we have played with these structures FSS. Now this is a engineering drawing which we have developed to develop this GNSS multi-band antennas. I need to go in detail, but you can find out the dimensions. All dimensions are given in mm. Now, if you see FSS dimensions, these all FSS dimensions are nothing but same theoretical formula of microstrip line. If you elongate, the length and width will be deciding the value of L and C, and based on the value of L and C, we will be able to say how much the resonant frequency. Now this is top surface, this is bottom surface. You got all combinations of different FSSs and very compact in size 102, 105 is the ground plane, but the PCB is having 25, 25. The dielectric size is 25, 25 and 4.3 mm only. This is what formulation I was talking about. So the resonant frequency here is depending on the dimensions. And the here I think there is some typing mistake here. Epsilon r under root also must be there. So Fr is equal to C upon 2 pi under root epsilon r and then whole under root m pi here there is some typing mistake. Under root epsilon r is must be there. So m pi by a whole square plus n pi by b whole square plus p pi by d whole square. This is the basic formulation of designing a rectangular dielectric resonant antenna, where c is velocity of light, epsilon r is effective permittivity of the material being used. If I use R2 it will be 2.2. If I use FR4, 4.7. M, N, P are very crucial parameters here. A, B, D are the X, Y, Z dimensions. So M, N, P are number of half-wave variations along X, along Y, along Z. These indices will control the mode theory. So to excite fundamental mode or higher order mode, either TE or TM or TEM will be depending on these values. There is a well-known equation which is characteristic equation, has been modified to transcendental equation, will be applied here. And based on this formulation, we will be able to say at what frequency our antenna will resonate. So here also the parameters of dr dimensions and dielectric constant value, that is epsilon r, with the help of these m and p, will decide at what frequency I want to operate at. If you see here, this is very important. ENG metamaterial annular rings which we have used to control our dimensions. So this ABD has been now made. So far these ABD were only dependent on this FR which is being given here. This FR was dependent on ABD. Now we have introduced a new research parameter which is ENG, and now this parameter of ENG is regulating the ABD dimensions. I will be able to make or change these dimensions to lower values or control these dimensions ABD with the help of introducing a concept of ENG, and that ENG is also known as ZOR. ZOR is nothing but zero order resonance. So here the value of R1, R2 are the radiuses, epsilon R are the materials which I am using, C is velocity of light again. Hence, I say the initial formulation which was used to develop rectangular DRA operating and fundamental mode is now being controlled with this ENG or FSS or metamaterial structures. The design formulation being used to develop ENG structure is explained here. N is equal to 1 upon KD cos inverse bracket 1 upon 2 S21 1 minus S11 plus 1 plus S21 square, and Z for this particular will be 1 plus S11 square minus S21 square upon 1 minus. This is the formulation, standard formulation being used to develop ENG. ENG is nothing but epsilon negative structure, where epsilon is given with the help of NYZ and mu is given by NZ. The K and D are wave vectors and distance respectively. N is refractive index and S11 and S21 are reflection and transmission coefficient. Epsilon here is specifically termed as permittivity, and Z will be the impedance. So to design ENG properties, we need to play with the structure. Now, SRR is a split ring resonator. We are already familiar with FSR structures, that these structure will possess inductance and capacitance, and based on the gap and the length of the split ring resonator, the resonant frequency or excitation at what frequency it will resonate is decided with this formulation. That is the dimensions. Basically we are dimensions, and where the dimensions are being placed. So L effective, C effective are the effective inductance and capacitance values. These values will be decided based on the structure. SRR will have length as well as gap. Gap generally decides the capacitance value, and the length of ring will decide the inductance value. So, with the help of this graph, we are able to present you that we successfully implemented the structure to introduce a concept of ENG. Here, we are able to get at frequency 0.8 negative permittivity, at 1.8 again negative permittivity. These are our operating frequencies. So similarly, we have made a structure in such a way that whatever my operating frequencies are there, I'll be able to introduce a concept of ENG, or I'll be able to bring out the value of permittivity at that particular operating frequency to negative. In this multi-band GNSS antenna, these are the structure has been utilized. All the structures represent a FSS, frequency selective surface. Here, some are rectangular, some are circular in nature, and based on those configuration, we are able to get the resonant frequency as depicted in the graph, that each structure is displaying here. If you see this structure, it has this frequency. If you see the lower structure is resonating at this frequency. If you see this structure is resonating at this frequency, all spanning from 1 gigahertz to 1.8 gigahertz. So if you see circular SRR, it is resonating at this frequency. So here, depending on the R dimensions, I'm able to get the resonant frequency on these different resonant modes, which covers the entire L1 band to L5 band. This is the hardware which is being shown to you. The hardware results within the anechoic chambers has also been taken, and these are the representation L1 band, L2 band, L3 band, L4 band, L5 band, and here are the RSCP being obtained, which is being represented with the help of XL ratio. Efficiency, this plot is showing that L1 to L5 band has efficiency greater than 90 for all bands. Now if you see initially, but I told you the gain of this antenna was brought to 9 dBi. Here we see the gain obtained from L1 to L5 band is above 3.5 dBi, almost all bands. Then the impedance is almost matched for all these bands approximately. These are beautiful representations by which I am able to see the radiation patterns or radiations emissions from rectangular DRA, from the antennas formed by frequency selective surfaces. Now here you see that and I have shown with the animations that the radiations with DRA is very good and directional oriented here. This is the radiations obtained from rectangular SRR. And same plots are also being depicted in XZ and YZ plane. But this is more clearly visible that with the help of 3D animations, I am able to represent how my radiations are taking place at 1226 point or 1.2276 gigahertz. These are the radiations which is depicted by circular SRR. And same plots are being also shown here XZ and YZ. If you see here, this is a 3D plot of radiations obtained from rectangular SRR. And same is being also represented here XZ and YZ planes. There are two rings. This pattern is specific to the other rings on here. And these are the electric field pattern which are very important to understand that which mode is being excited in X direction, which mode is being excited in Y direction, which mode is being excited in Z direction. Maybe if you see here, Ez by X, there are three number of half-wave variations in X direction, and there is only one number of variation in Z direction. Similarly, here, if you see here, this, if I see this plot, so there are two half-wave variations in Z direction and there are three half-wave variations. If you see here, there is only one half-wave variation in X as well as Z. So depending on the field, E field pattern plotted, we will be able to interpret that how many number of half-wave variations are there in particular direction, either in X direction or in Z direction or in Y direction. So number of half-wave variations will be represented by the number of modes exist in that particular length. Maybe A, X means A, Y means B, Z means D. This particular animation specifically being represented to capture your circular field. If you observe it more precisely, you will see that E field is rotating in clockwise. So when I say clockwise, it is RSCP. When I'm this depend on totally on the designer. The designer can rotate this field in anti-clockwise. Designer can rotate this field in vertical orientation. Designer can rotate this field in horizontal orientation. So the rotation of electric field will signify whether it is circularly polarized, whether it is elliptically polarized, whether it is horizontally polarized, whether it is vertically polarized, or it is right hand circular polarized, or it is left hand circularly polarized. So all these polarizations will be depending on how you create rotation in the field, and it is depending on the designer, how the designer is being proposed. So here it is clearly showing that the fields are rotating in clockwise direction, and these clockwise direction fields are known as right hand circularly polarized fields. These are RSCP. Now, if you see, these E fields are rotating clockwise, and this clockwise rotation has been achieved using the Z shape slot being created at the ground plane. If you keenly observe, more precisely see here, there is a one arm, there is a this arm, and there is another top arm. We have purposely made this top arm elongated as compared to the bottom half in Z-shaped slot, so that the dominance is taken over by longer arm, and that is why the the field of rotation is created, RSCP. If I make this elongated, this shorter, my dominance of electric field rotation will be taken by this arm, and the field will now rotate anti-clockwise. So this is depending on the designer. You can clearly observe the field's rotation here. I'll play it again. So which direction the field is rotating, clockwise or anti-clockwise? It is clockwise. Here it is better way represented with the arrows, that because of the structure or slot structure being presented in this manner, it is representing you and showing you a clockwise orientation of the E field. Beautiful diagram. So we will see that the flanked port designed here is representing a frequency selective surface of different dimensions in terms of radius. And we, if we see and go back, see the formulation of split ring resonators or annular ring resonators, or the circular resonators, depending on the formulation which we have depicted earlier, the resonant frequency will occur. So R1, R2, R3, R4 will control different frequencies in this particular circuit port. This is the total process being depicted. Initially, if you see the size of DRA, A is representing 60 into 60 into 40, and if you see the dimensions being represented in figure C here, see the dimensions had been turned into 25 into 25 into 4.3 mm cube. So you can just see the initial dimensions were 60 mm, 60 mm into 40 mm, and same using ENG concept, this has been reduced to this. So this is a great research achievement, that we are successfully able to design using concept of ENG to compact size of GNSS antenna, which was not possible without the use of high dielectric constant material being involved, which were not available in India anywhere. And we were purely depending on the foreign countries to procure these high dielectric material at very huge amount of cost. So cost and non-availability made us to think of alternate solutions to devise these DRAs, which will be used to develop GNSS antennas in compact and low profile category, were achieved using low dielectric Indian origin materials. So material was a crucial issue for us to design these antennas. But now we have capability that small size antenna can also be designed at any frequency from the existing dielectric alumina material, and with multiple bands being provided. So two achievements I am showing from this particular diagram, that number one, I am able to get all-in-one solution in one antenna. Second is I'm able to get miniaturized and low-profile dimensions of ceramics or dielectric resonant antennas in the same design. Here, this is another. So here, if you see, we are able to represent you a Navik, which is 2.49 Wi-Fi band, and with all other 5 band, WiMAX band. So everything is available in one compact solution. This is our achievement, that we are able to propose a all-in-one antenna which will be utilized for all navigational needs, maybe for autonomous vehicles, maybe for aeroplanes, maybe for our watch, maybe for any IoT device. So this is a solution, all-in-one solution available with us, that we are able to cater to compact, low profile antennas today because of FSS structure or ENG structures. These are the few patterns being depicted for your know-how, that how the radiation pattern of these structures look like at different frequencies. This is 2.4 gigahertz. This is at Navik frequency 2.49. This is at Wi-Fi frequency 5.8. This is at L5 band. These are the same fields. Now, as far worldwide is concerned, there are Indian origins which are working in these domains, but rarely they are able to provide us all-in-one solutions. As far as India is concerned, Bell, HAL, ECIL, Astra Microwave, Adani, these are the few manufacturers which play as far as foreign, lot of people are there. Now, this was all about the product which we have designed to apply for GNSS features. We are coming up with another solution which will be crucial for 6G communication. We are assigned a task to develop 6G antennas which will have reconfigurability being introduced by using fluid element. The fluid element will be microprocessor controlled, and these fluids will have the temperature dependence characteristics. They will flow in fluidic channel. The fluidic channel will make them to probe when stressed. When stressed, probe will be out. When they are static, probe will be inserted. So these are state-of-art architectures, and they will have the metal liquid as an replacement of the metal or ceramic, and the fluid will not be static. You can rotate the position of fluid depending on the availability of the signal. For example, this is iPad. You can replace this iPad with the help of mobile. Whenever the tower signal faces some problem, poses some problem, your antenna will go to that particular position from where the tower is able to fetch you good amount of signal. So automatically the fluid element will rotate into that particular direction. So state of art antenna will be governed by the fluid antennas, which is new technology and yet to come in the field for operational capabilities. We have just started working on this antennas because we are being funded by DOT amount 1 crores to develop these antennas. These are the few snapshots. We conducted one 2 months training for our BTech students to design different GNSS antenna and lab. So these are our BTech students working in these domains. Uh, One more beautiful work which we have taken up is using this multi-band GNSS antennas to harvest energy, RF energy, which is available around the clock, because you see that GNSS frequencies are available round the clock. If it is possible that we harvest this GNSS signals using uh, the RF circuitries and antenna, and make your low power sensors to act or to do not have any cells, they can operate directly from the ambient environment. So this is another field of working in GNSS category. With this, I like to conclude. These are the few conclusions I have mentioned here, but I'll not go in more detail. I like that you people should ask few questions based on the presentation which I have made. So this is all which I wanted to tell in today's lecture. Thank you very much. You may raise questions based on the inputs given to different audiences.
Participants, you can ask the question. You can drop your query in the chat box. Sir, for fluid antenna, how much gain is desirable and
Swati,
what material? Yes, sir.
you are working in this area?
Sir, I'm working for the antennas, sir, wideband antennas.
Okay, okay.
Yes,
See,
sir.
the fluid antenna is same antenna. Whatever is antenna available in your mobile presently, these are metallic antennas. Maybe inverted F or whatever. So gain will be same. Gain is not a problem.
Okay.
Hmm. Only in addition, you are getting reconfigurability and direction sensing.
Okay, sir.
Hmm.
Yes, Abhishek, we are enabling your mic. Please give us a 1 minute.
You can unmute.
Abhishek, you can ask the query. You can unmute and ask the question.
I think he's not audible. You can read his questions. You can take them on the
Yes,
text
sir.
as text. I think there is no question. Huh?
Actually, participant is trying to ask the question. There is some problem. Please give a minute,
Okay.
sir.
Abhishek, kindly text your question in the chat box if you are not able to unmute yourself. Kindly write your question. Sir, Raju sir.
Ah, huh.
Sir, the
Sir, the
question is
question.
question is that the participant is working in energy harvesting. How
Hmm.
FSS can be used for it?
Yeah, I have shown you the design. You can develop multi-band antennas and then integrate with the energy harvesting circuitry to double or triple your input energy, and accordingly you will get harvested energy more.
And Filtena is better or absorber for it?
No, 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 both. You can play with both.
Okay, sir.
Mm.
So the next question is, reconfigurability is possible in metallic antennas also, sir. How fluid antenna is better than that?
Actually, there is a problem in the circuitry as far as metallic antenna is concerned. You get lot of switching networks, which is being eradicated in terms of fluidic antennas. There is no switching element being involved.
Okay, sir. Sir, one question from the participant Piyush. How FSS and AMC differ?
AMC is again, I think he is not able to understand my concept. Initial slide I have shown FSS being used as antenna, FSS being used as absorber. So AMC is a concept of absorption, and FSS, if he is using at lambda by 2, is antenna.
Any more questions, participants?
And you can provide them my email ID. If they are not asking, they can ask anytime. That is not a problem.
Yes, sir. Sir, is it easy to fabricate the fluid antennas?
We are still working on this because it is really difficult task to fabricate fluid antennas. But we will be.
Any more questions?
Hello,
Yeah,
good afternoon, sir.
good afternoon.
Sir, what is the need of placing metamaterial at the back of antenna?
Okay, DGS. That is DGS concept.
Sir, why we are using?
You are creating slot for stop band. See, when you develop multi-band antennas, you need to go for frequency ratio. And to have good frequency ratio, you need to have isolation from the undesired bands. And DGS will help that. Any other questions?
Sir, I think now no more questions are there, sir.
Okay. Okay, thank you, sir.
On behalf of MNITs and EACT Academy, sir, thank you very, very much, sir. The
Okay,
session
thank
was
you.
very much fruitful to all of us.
Okay, thank you, Swati.
Thank you, sir.
So I'll exit now.
Yes, sir.
Okay.
Dear participants, the next session will be the hands-on session from 2:30 p.m. You are requested to kindly join on by time. Yes, Abhishek, email ID will be provided to you.